Hello, everybody. Welcome to the IPv6 webinar that I'm doing. This is my first one ever, and I'm pretty excited about it, actually. So what I want to talk about today is taking the fear out of IPv6. Now, one of my experiences with IPv6 is that when I talk to network engineers and my own personal experience over the last 5 years with IPv6, what I find out is that everybody's a little bit afraid of it, and the documentation out there for it is lacking at best. What I usually find is that when I try to read about IPv6, it tells me about a lot of really cool features about IPv6, but a lot of them that I either can't implement, I don't know how to implement, I don't know why I would implement them, and there's a reason for that, and that's because most of it we're not quite ready for that level of IPv6 in our networks. However, does it mean that people are not running IPv6? No, absolutely not. There are some pretty substantial and large environments running IPv6 right now. So let's take a look at some of the fears of IPv6 that I've heard about over the last several years. And one of them is complicated. Well, no doubt it's complicated, right? I mean, of course it's complicated. If you think about data networking in general, data networking in general is a bit of a mystery. I teach data networking at a technical college here in Madison, Wisconsin. And, my experience with that is IP version 4 is complicated, right? The first things that I teach my students is how the IP version 4 IP address works. Well, if we think about IP version 4, that is obscenely complicated, right? Because in 94 or 96, we added that whole network address translation plus private addresses plus the subnet mask. And we basically hacked our IPv4 address to make it about as complicated as we could. All right, so is IPv6 more complicated than 4? Some areas, yes. Other areas, absolutely not. Second, it's going to break your network. Well, yeah, it can, but I can also have an IP version 4 network that breaks. All right, I've been involved in plenty of IP version 4 networks that were set up by people that didn't understand how IP version 4 worked, and the network broke. So we have these same risks in IPv6. It's not something inherent of IP version 6. It's more so it's inherent in the administrator dealing with the protocol. Another one I've heard numerous times is you should never, ever run a dual stack environment. Well, what's dual stack? Well, dual stack means that we're going to run IP version 4 and IP version 6 at the same exact time in our network. Excuse me. So should we do this? Well, absolutely. If we look at the public internet itself, the public internet is running both IP version 4 and IP version 6 at the same time. So we can send packets across the IP version 4 internet at the same time we're sending packets across the IP version 6 internet. All right, so is a dual stack a big problem? It could be if we don't know what we're doing, and it could cause problems. But once again, this is an ignorance of the administrator more so than something inherent in the protocol. As a matter of fact, if you think about it, if you've been in IP long enough, you'll know that back in the 90s, we almost exclusively had to run a dual stack environment in our networks. And that's because with Novell network operating system back in the 90s, we needed IPX SPX to run on our networks. Well, IPX is the layer 3 protocol for Novell. SPX is the layer 4 protocol for Novell. And we had to run that side by side with IP. All right, so if our workstation wanted to communicate with the Novell file server, it had to use it had to use IPX, and if your workstation wanted to talk to the public internet, it had to use IP version 4. So dual stack is nothing new in data networking. It's just within the last 15 years we kind of got out of habit with it. Does that mean that there doesn't cause problems with two protocols running at the same time? Yeah, if you don't know what you're doing, you're going to have issues. All right, here's another fear. IPv6 is insecure. Well, IPv4 is insecure. Is IPv6 more insecure than version 4? I actually don't think so, because we can still implement firewalls, with IPv6. We can still implement other procedures in order to secure IPv6 just like we do IP version 4. All right, another fear here, or maybe this is not even acknowledging the fear or hiding from the fear, is that I don't need to know IPv6. My company's never going to migrate to it. It's an expensive situation. We don't need it. Everything that we do runs on IPv4 just fine. Well, great. That's a great attitude to have. We call that the ostrich head in the sand syndrome. The reality is do you have to use IPv6, especially if you're in the United States or Europe? Not right now. But what we're going to see is within the next 5 years or so, we're going to see organizations, especially in Asia and other developing areas, where there is no more IP version 4, and we end up with a large organization that's exclusively on IPv6. And if we're going to do business with that organization at some point in the future, we're going to have some kind of IPv6 connectivity. All right, so it's a good idea to start diving into this now than later. The last one here is it's new. Yeah, it's new. It's scary. It's a whole new thing to learn and deal with, and a whole new set of protocols to deal with. And this can be a little overwhelming because most of us know, if you've worked in data networking or you have even a little understanding of how IP and IP routing work, this is a pretty complicated and sophisticated system. So learning a new one can be an overwhelming challenge, especially if you've been in industry for a while. All right, so let's take a look now and see. Well, here's our agenda, all right? This is what we're going to do to get over these fears. Okay, so first of all, I've kept this presentation to just the basics. All right, I'm not going to get into all of the definitions of all the different address types, of all the different little nuances of it. What I want to do here is give you the education so that you know exactly what you need to make an IPv6 network work, and then later on you can use that working IPv6 network to figure out how all of the rest of the stuff works. Okay, so first thing we're going to do is we're going to look at the IPv6 address format. Some of you may have looked at this and are familiar with it. It's one of the easier logical things to explain. So I will go through the basics of the IPv6 address format. We're going to examine this enormous size of the IPv6 space. And this is really important about examining the size because this is where we have one of our fundamental differences between version 4 and version 6. We have a lot more space in version 6, and by a lot more, it's a scale that most human beings cannot fathom in their own brain. All right, so we have this enormous scale of IPv6. We're then going to talk about some basic IPv6 design rules with respect to assigning networks, network addresses to network links in our environment. Excuse me. I have allergies here. You know, Madison is just full of flowers right now, so my allergies are crazy. So sorry about my little bit of a hoarse voice. And then last, I'm going to show you how we can connect to the IPv6 internet. As a matter of fact, there's a resource you can use for free that will let you get an account and get you hooked up to the IPv6 internet and actually give you a massive amount of IPv6 space to play with. And then last, I'm going to do a really simple demonstration of an IPv6 only network. Okay, so I'm going to turn off all of my IPv4 configuration and just allow IPv6 to work. And then we're going to jump online. We're going to jump on the internet and see a little bit of what we can get to and what we can't get to. And this will illustrate a point about how IPv6 connectivity works. Good. So first of all, the size of this address. The size of this address is absolutely enormous, okay? It's 128 bits long. Our IP version 4 address was 32 bits long. So this has 4 times as many bits in it. All right, so it's 128 bits long, 32 nibbles. What on earth is a nibble? Some of you might know what that is. A nibble is half of a byte, and a byte is 8 bits. All right, so we have 8 bits in a byte. Half a byte is a nibble. How clever. And so we have 4 bits in every nibble. The nice part about this is our IPv6 address is written in hexadecimal. And every single hexadecimal value here is worth 4 binary bits. All right, so if we add up, if we count these numbers here, we'll find that there's 32 hex values in our IPv6 address. Each one of those hex values is worth 4 bits. Okay? Another way we talk about this is the hex text. Okay? In IP version 4, we talk about the 4 octets, right? The 4 sets of 8 bits of numbers. Here we talk about 8 hex texts, and we separate our hex texts with colons. So 2001 colon, 0DV8 colon, 0000 colon, and so on. All right? Each set of 4 hexadecimal values here is worth 16 bits, right? 4 hexadecimal values, 4 bits per hexadecimal value, 16 bits each. So every 16 bits we put these colons. All right. Now, when I first looked at this, the size of this address and thinking about how I do subnetting in binary, and having all these binary bits and this enormous address was overwhelming to me. All right. Let alone what happens when I have to troubleshoot, and when I troubleshoot, I have to type in ping 2001 colon 0DV8 colon 000 colon 000 colon, and so on. This is how horrific. Who wants to type all that in? Well, what we're going to find out is that there's ways that we can make this much, much simpler in the long run. And actually, after playing with IPv6 for a while, you end up finding out that it's actually a lot easier to work with than IP version 4. Okay? So, let's move on. Let's move on here. Reading and writing IPv6. All right, so we're going to take that example of the IP address that I had on the previous slide here, and what we're going to do is we're going to show how we can shorten writing out this address. Okay, so first of all, what we need to do is we can take out any leading zeros in any individual hextet. Okay, so what this means is we can shorten our address right away to 2001 DV8 to 8D 0085 52F5. And the way we're doing that is we're saying 0DV8, well, that's equivalent to DV8. 0002, that's equivalent to 2. 008D, that's equivalent to 8D, right? 0000 is just 0. And so on, right? And this is the same idea that we use in regular math. If I say, well, I have a number 1, and then I say, oh, is 1 the same as 01? And is 1 and 01 the same as 001? Yeah, they're all the same. It doesn't matter how many zeros we put in front of our number. It's always the last value that we care about. So here all we're doing is in every hextet, we're just eliminating the leading zeros. The second thing we can do is we can eliminate groups of zeros together with a double colon. We can only have one double colon per IPv6 address that we write, right? Because the double colons are going to break apart the address and put in a certain number of bits in there that are all zeros. And then we can use the rest of the numbers in our address to extrapolate back how many zeros should be there. Well, if this sounds complicated, it is in the beginning learning it, and there's some unusual rules there with our double colon in that we can only use it once within an address. But the nice part about this is that that double colon, for the most part, ends up getting put right in between our network portion and the host portion of our address. All right, so we can start using this double colon really effectively in a little bit. It's going to shorten up our address and make it a lot easier to work with. So all I did here was take the 2 zeros here, and we just replaced that with the double colon. So let's take a look now at the difference between our network portion and the host portion of our address. Okay, in IPv6, we have a network portion, and then we actually call our host portion the interface identifier. All right, so our host portion is the interface identifier. And what we're going to find is that whenever we apply an IPv6 address to a group of devices, we're going to use a /64 mask. All right, so 64 bits are going to be in the network portion, and 64 bits are going to be in the host portion. Do we have to use a 64-bit mask? Absolutely not. We have essentially the same freedom with our subnet mask in IPv6 that we do in IPv4. We can move that subnet mask anywhere we want, all right? So I can move this line here. Right now the line is at 64 bits into my address. I can move that over this way, closer to the interface identifier portion, or move it into the network portion. It's completely legitimate to do, but what you're going to find out is that there is an elegance and a brilliance to using /64s as the only subnet mask in your entire network. All right, so whenever you apply an address to an interface, we're going to use that /64. This is my version of the, quote, right way to do it. In data networking, there is never really a right way. If it's effective and secure and serves your users' needs, that's outstanding. My goal in this presentation is to show you how we should be keeping IPv6 very, very simple so that it's really easy to troubleshoot. So let's move on here. So now when we apply for IPv6 address space from our internet service provider, right, depending upon the scope and the size of our company, if I'm a smaller to medium-sized company, my ISP is probably just going to give me a /48 network IP address for me to use. Excuse me. So my ISP is going to give me this /48. So they may give me 2001 DB8-2 as the first 48 bits. And what that means is I cannot change those first 48 bits anywhere in my network. All right, so 2001 DB8-2 /48, those are my network addresses. Then what I can do is I can assign the /64 for my to get my host portion to be 64 bits. And what that leaves here is it leaves me 16 bits to subnet. All right, so I have 4 hexadecimal values here, and I have 16 bits here to subnet that. That means that these 4 values can be from 0000 to FFFF. All right, and what that means is that I can get 65,536 /64 subnets for every /48 that my ISP gives me. Wow, right? This is just the default one that your ISP is going to give you. Later on, I'm going to show you a free resource where you can get up to 5 /48 IPv6 address spaces for free. All right, so I'm going to show you later where we can go get 5 of these /48s for free so you can go play with it. All right, you don't have to set up production networks. You can set up some small isolated networks that you can just play with and see how this stuff works because it's really slick. And once you get used to it, you can start finding ways to actually implementing this into your own networks. So here's one thing that is really important that we have to get through our heads. Okay, in IP version 4, we were incredibly efficient with how we handed out address space. Okay, and in IPv6, we don't need to be so efficient and uptight about handing out IPv6 address space. So let's take a look at an example here. If my starting mask for an IPv4 address was /8, all right, so we have a class A address, 10.0.0.0/8. Well, the number of /24 subnets I can get from that is 65,536. All right, I have 16 bits to work with there to get my /24s. The problem here is that only gives me 254 host addresses for every single IPv4 network. Well, 254 is a fine number, right? That'll get us most of what we need usually. However, there's circumstances, and I've been involved in plenty of them, when a /24 isn't the right mask because you need 500 devices or 1,000 devices, right? But once we start getting beyond 1,000 devices, now we have other issues, right? And those have to do exclusively with Ethernet and how that broadcast domain works. What I'm getting at here is IPv4, yeah, we can easily get 65,000 subnets, but we're only going to get 254 hosts per subnet. If we take a look at IPv6 with our /48, we can get 65,536/64 addresses out of that. And what that does is it gives us 18 quintillion hosts per /64 subnet. This is an obscene number. I mean, truly obscene number. All right, this is multiple factors of the number of people on Earth. So any one subnet could give every human on Earth several IPv6 addresses. So when we're talking about wasting addresses here, in IPv6, we've built it to accommodate lots and lots and lots of host addresses for every subnet. Does this mean someday we're going to see an Ethernet network with 18 quintillion hosts on it? Good Lord, I hope not. All right, I hope not. That would be a complete mess, and the network would be overwhelmed with control traffic. So we really wouldn't do that. But the point here is that we never have to worry about changing our mask on our network because we'll always have enough host addresses for our devices. Okay? In a little bit, I'm going to go in to show you about wasting addresses. But before we do that, let's take a look at how we subnet this a little bit. So before we get into the subnetting, let me give you an idea of the scale of the size of addresses that we have available to us. All right, so the Internet Assigned Numbers Association, the IANA, they are the worldwide administrator for IP version 4 and IP version 6 addresses. And what they will do is they will allocate then address space to each of the regional numbers groups throughout the world. All right, and in North America, we have ARIN is our numbers registry. They hand out the IPv6 addresses and the IPv4 addresses to Internet service providers, and then the Internet service providers are going to hand those addresses out to their customers, which may be you, or it may be another Internet service provider before it gets to you finally. Either way, ARIN's initial allocation of IPv6 addresses, this happened in 1999. The initial allocation was 2001/400:23. All right, and what that means is that we have a range of addresses, of /64 addresses, from 2001/400:00 through 2001/5FF. This is a lot of networks. As a matter of fact, this is 2 to the 41st networks. What is that? Millions, billions, trillions. 2.2 trillion networks we have available with just ARIN's initial IPv6 allocation. All right, and all the registries around the world are going to have essentially the same IPv6 allocation. To give you an idea, the entire IP version 4 address space is 32 bits. So if we include all of the unusable addresses in there, our 127s, the multicast, have only limited utility. The experimental address range has no utility. So if we look at all of the address space for IPv4, it's only 4 billion addresses that we have available. Here we have 2 trillion. This is actually 512 times the number of IP version 4 addresses. So just for ARIN, the North American group's initial allocation of addresses, they have 512 times more networks available. Actually, that's not even true here. It's even bigger than that, right? We have 512 times more networks available than we did with IP version 4. All right, and this is actually not even an accurate description here, because down here in 2 to the 32nd, I'm saying this is all of the IP addresses, right? This is all of the IP addresses. Here, this is just the networks. And then on each network, we can have our 18.4 quintillion hosts per subnet. So right now we're approaching, with just this initial allocation, we can hand everybody on Earth, well, 2 trillion people, yeah, we can hand everybody on Earth an IPv6 network address, which this is starting to get to be really, really kind of cool, actually. The size of this is beyond our ability to imagine. So here's the rest of the ARIN IPv6 address space that's been allocated. In 99, that's when they got the 400/23. Then in 2003, they got the 1800/23, essentially doubling the space they already had. Then in 2005, they got the 2610 address space here, tripling their space from before. And then they added in this 2600:0/12, right? That even has a smaller network portion, right? As a matter of fact, that's only the first three hex values here. So the division that we get here is after the first 3 hex values, we get everything after that, from bit 13 to bit 64 to create network addresses. So this is just an unfathomable amount of networks. All right, so do we really need to be conserving these? Probably not. Before we look at how we're going to conserve and design our subnet masks on our network, let's take a look at how we're going to distribute this /48 address that we received from our ISP. All right, so I'm just taking a very generic example. Every single network on Earth is different. You're going to have different requirements, different design strategies. You, as the network administrator, are going to have to choose how you do this. But what I want to do is give you some guidance into how we should do it to make it simple and organized. All right, because IPv6 has this tremendous ability to be very organized and very efficient, and it'll make your job as a network administrator incredibly easier. All right, so we have 3 regions here. So I have 3 sets of buildings. One might be in Chicago, one might be in Denver, one might be in LA. And what we would do here is we would take our /48 and we would break it into smaller pieces. All right, so what I've done just for the demonstration here is I said I'm going to assign each building here a /52. Okay, a /52 that's within the range of my /48. And what that means is that every single network in all of my buildings here, in all 3, they're all going to start with 2001 BB8A. Okay? For this first building here, I'm going to say 2001 BB8A 0:52. So this now will be all of the networks that we have available for this particular facility. Then when I go assign these to individual networks, maybe my first floor network or the lobby network is 2001 BB8A 0/64. And then the first floor is 2001 BB8A 1/64. Second floor is 2/64. Third floor is 3/64. Right? Notice how these first 3 numbers here are never going to change. And that's going to be true in our entire network. In my experience, after you type these first 3 numbers about 30 times, man, those numbers are burned into your brain. You know what they are. Right now, all you're dealing with is this last number, the 4th hex tech. That's the only number you really have to worry about now. And we can make that number just count. 1, 2, 3, 4, right, all the way up to FFFF. For our second building here, we can do the same exact thing, all right? Except this time, instead of making the first hexadecimal value here a 0, we're going to make the first hexadecimal value a 1 in our 4th hextet. All right, now for our second facility, our network addresses for each floor or each area of our network, the /64 addresses now are 1000, 1001, 1002, 1003, and so on. All right, same thing for our third building here. This we can assign 2000 in our 4th hextet, right? And now we can count our addresses there. This gives us this fantastic ability to have a huge range of networks for any facility that we have out there and still have plenty of space for all of our facilities. Let's take a deeper dive into this, and I'm going to show you the binary. All right, and if this binary goes over your head a little bit, don't worry too much. I do have a whole series of CCNA data networking training videos, and one of them that I go through is IPv6 binary and hex, and I also go through IPv4 and how binary works with IPv4. And all of those skills lead you right to here. So I highly recommend you go check out those videos I have on the Pluralsight website. Even if you're not interested in your CCNA, I did not design those videos as a boot camp for the CCNA. I designed it with all the information you need for the CCNA, and then I put in there, I put a spin on it so that you can actually use and apply the stuff in your real network. Okay, so let's look at the binary. We can go do a deep dive into it later if you want. So just hang tight with me if you don't understand. So what I did here is I took my first building's /52 address, and that was 2001 DB8A0000. And then what I did right below it here was I kept the first 48 bits in the hexadecimal notation, and then I converted these last four values here, these last four hex zeros, I just converted them into binary, all right? So I just expanded those out from 4 hexadecimal values into 16 binary bits. And the binary is shaded in the blue here. All right, so our /52 is going to fall right here, okay? It's this line here. And the way I got that was we have 16 bits in our first 3 hextets, right? That's a 48 bits total. And then if I start counting in binary, we have 49, 50, 51, and 52. So really what I did here is I isolated this first hexadecimal value in my 4th hextet and said that value represents this building that I'm going to assign addresses to. And then when I start counting my addresses, notice that 0000 is the first 4 bits in that 4th hextet for every single address here, right? And then if I look in the next part here, I have all zeros, then 000001, then 000010, then 11, right? If we convert these back to hexadecimal, what I end up with is 0, 1, 2, 3. Here I have F, 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 right? So when I'm assigning these, really, I'm saying for this particular region of my organization, I can have any address between 0 and FFF as my networks. That gives me about 4,096 networks to work with in each one of my facilities. And because I have 4 bits that I'm using to identify the facility here, that 4-bit hexadecimal value right here, this one, this one, this one, because I'm using those 4 bits, I could have up to 32 different buildings or areas, and each one of those areas can have 4,000 networks. All right? This is a really beautiful way to organize your network into very specific pieces. All right? Hopefully that all makes sense. So let's jump in from here, from this subnetting part and organizing your network. Let's take a look now about why we would want to use that /64 everywhere and not jump back to using a really efficient address scheme like we do in IPv4. So let's take a look at an IPv4 point-to-point link. All right, an IPv4 point-to-point link here. Typically, we use a /30 mask, right? And that /30 mask gives us 2 bits in our host portion. Since there's 2 bits in the host portion, that gives us 4 addresses total. We have 10,000, which is our network address, 10,001, which is our first host, 10,002, which is our second host, and then our broadcast address is 10,003. All right, 2 host addresses. This is brilliantly efficient. all right? You can't get much more efficient with your use of IP space than you can here, right? There is one other way we can do this, and we can use some trickery that violates the protocol, right, and just use 2 addresses and a /31, right? I don't particularly like that in IPv4, but sometimes you have to. But regardless, whether we're using 2 addresses or 4 addresses for this link, it's pretty darn efficient. Well, let's take a look at IPv6. Now, earlier I said we use /64s. I said we should use /64s in our environment to make it very simple to use, all right? Very simple to use and support and address and whatnot. Well, the problem here is that if we're stuck in an IPv4 addressing design mindset, what's going to happen is we're going to flip out when we see that we just gave this network that will only ever have 2 hosts on it. We just gave this network 18.446 quintillion host addresses that it can use, which means we've wasted 18.446 quintillion addresses, right? Oh my gosh, oh no, what's going to happen, right? We wasted all these addresses. Shame, 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 you bad, inefficient network engineers. Well, no. All right, let's put this into perspective, okay? Let's take a look at a tiny little dual stack network. So we're going to look at this very tiny dual stack network. It's just 2 routers and then some client hosts. And what we have here is we have this point-to-point link between our routers that has 2 hosts on it. And we're using 10.1.0.0/30 on that network. And then up here, we're going to use 2001 DB8A B:/64 for our IPv6 network for this link. And then on the other side, for our clients, we have 250 hosts on our network. We're using a /24 IPv4 address. We have plenty of IP addresses to accommodate our hosts. And then we're also going to assign our IPv6 here, 2001 DB8A A:/64. All right, so here, if we look at this and we draw a little chart, right, my /24 mask for IPv4 gave me 254 hosts. My /64 mask for IPv6 gave me 18 quintillion hosts. If I subtract 254 from 18 quintillion, I get 18.446 quintillion wasted addresses, right? The rest of these numbers are not even relevant because we have 18.446 quintillion addresses. Well, let's take a look at the /30, right? /30. We're going to use 2 host addresses in IPv4. /64, we get the same number of host addresses available. If I do the math again, I'm still wasting 18.446 quintillion addresses. As a matter of fact, I looked at the percentage difference of addresses that we're wasting on a network that has 254 clients versus one that we're wasting with 2 clients in IPv6, and I can't even get this number to calculate a percentage that's within 12 decimal points. So it's like 0.0000000000001% more wasted addresses. Big deal, right? Big deal. So let's use this idea of having this enormous host range and having the luxury of not having to be efficient with our IPv6 host address space or even our network address space. Let's use that to our advantage and make all of our networks /64 regardless of how many hosts are on them. All right? Because when we have /64s everywhere, it's going to make it real easy to summarize these addresses. It'll make it real easy to troubleshoot these addresses. And ultimately, it's going to cause no additional problems. Is this the right way? Is this the one right way to do IPv6? Absolutely not. All right? Could we make these networks in the middle here? Could these be /30s if we wanted? I'm sorry, not /30. Could we make these networks to be /126 if we wanted? right? That'll leave us 2 bits in our host portion. Yeah, we could do that. Except now we have a mishmash of subnet masks in our network. And we really didn't save us much. Okay? So I'm getting close on time here, so let's jump into this demonstration. All right? So I'm going to show you what I'm going to set up first, and then I'm going to show you how I built this connection to Hurricane Electric to get my IPv6 address space, and I can show you where you can go get your 5/48s. And then we'll hook this up, and you can see how the IPv6 addressing works. And then hopefully I'll have a few minutes left for some questions. So let's move on here. So what I want to do is I have the IPv6 internet hooked up, all right? And then I have an address from the IPv6 internet. This is my linking address. And that's 2001.470.C327:1:/64. All right? And I'm going to assign IP address :1 to F00. And then the gateway is already set up in the IPv6 internet cloud here to be :2. Okay, so it's these first 4 hex texts, and then :1 for this side, :2 for the internet side. What I'll do here then is on the inside of my network, on F01, I'll set up address 2001.470.C327:A, :/64. All right. So here's going to be network 1. This is going to be network A. All right. So let's jump into this. Where do I go here? I need to open up Google Chrome. And what I've done is if you go to he.net, I'm going to make this a little larger. There we go. If you go to he.net, what you can do is you can set up your own IPv6 tunnel, all right? That'll let you tunnel from either your workstation to the Hurricane Electric IPv6 internet, or it'll let you set up a router, all right? And you can actually set up a Cisco router, or if you have a Linux box, you can use that. There's a whole host of different configurations here. And you can set that up, and then it'll give you all the parameters to set up your tunnel to get from to get your IPv6 traffic out to Hurricane Electric, right? And essentially what it's doing is going to put your IPv6 packet inside of an IPv4 packet, send it to Hurricane Electric. Hurricane Electric will strip the IPv6 packet out of the IPv4 packet and send the message out on the IPv6 internet. So there's really no translation happening here between 4 and 6. We're just using an IP version 4 to create a tunnel so we can send IPv6 traffic through it, just like a VPN for the most part. All right, Hurricane Electric gives you all these parameters here. It gives you your tunnel endpoints and your connecting IPv6 addresses, and then it gives you your routed IPv6 spaces. By default, they give you a /64, all right? And then they also give you a routed 48, all right? And that /48 is the one that gives you 65,535 /64 addresses. So we get a lot to play with here, all right? The neat part about Hurricane Electric is that it also does, it also lets you automatically configure your device, all right? So once you get your account set up, you have to take a little test to learn about IPv6 addresses and make sure you know how they work. Once you take that simple little test, you get certified, then you can create your tunnel, and then let's say you have a Cisco iOS device here. Why didn't that work here? Well, that one's not working. Let's try a different one. Let me go back to my main page here. Oh, and of course it logged me out. So let me click on a different tunnel here. There we go. Okay, so what will happen is it's automatically going to generate the configuration for you that you need to install on your Cisco device. Or if you're using a FreeBSD device, maybe you're using some kind of free BSD firewall. You can select that, and it'll show you what commands you need to put in to configure that tunnel. You know, you have Juniper OS, we have Linux, we have Mac OS 10, NetBSD, OpenBSD, right? pfSense. So we have all these options here that we can automatically generate our configuration to put either on our workstation or on our router to get a real IPv6 address and actually start to play with this and start to make it work. All right, so I already have this set up on my end. All right, so let's jump into my router. I have a rollover cable hooked up to my router, so I'm going to connect there. And we're going to log in. And right now, this router is set up just for the base configuration. It has no IPv6 configuration and no IPv4 configuration. All right, so if I do show IP interface brief, we're going to see that there are no IP version 4 addresses on our devices. And if I do show IPv6 interface brief, I'm going to see that I have no IPv6 addresses on my device. All right, so let's go fix that. Let's take a quick peek at our drawing before I jump back into that. I have to get all the way to the end here. Sorry about this. There we go. All right, so what I want to do is I want to put this address, 2001-470-327A:1 on F01 and 2001-470-327-1:1 on F00. All right, so let's jump back into our router config. And now I'll go into interface fast Ethernet 00. All right, this is my connection to the internet. All right, and here I'm going to say IPv6 address 2001-470-C:327. And that is 1:1/64. Perfect. Now I have my IPv6 address on that interface. We'll do a no shutdown. All right, I'm also going to configure INTF01. This is the interface that connects to my client. I'm actually going to disconnect my client here and plug it into F01. So now I'm hooked up just like my drawing showed. And here I'm going to say IPv6 address 2001-470. See, I have fat fingers, and look at the mess I'm making here with this. 2001-470-3C:327. Right, all those are going to start the same. It makes this really pretty easy. But we have A:1/64. All right. So now I have an IPv6 address on both of my interfaces. I'm going to do a no shut on this interface. And the last thing I need to do here is I need to turn on IPv6 unicast routing. All right. By default, IPv6 unicast routing is off on Cisco devices. So you have to turn that on in order to get your IPv6 to route traffic. The other thing we need to do is we need to create a default route. All right. If I look at my IPv6 routing table right now, I'm at the wrong prompt. Show IPv6 route. We'll see that I have a route to my network connected to fast Ethernet 00. I have a route connected to fast Ethernet 01, but I have no default route. All right, so I need to configure that, and I can create that with a static route, IPv6 route, and then I say :/0. And what that means is take all 128 bits of the address and make them 0 and have no network mask on it. So all the bits are open host portion. This is equivalent to an IPv4 IP route 0000 space 0000 and then with your next hop address. So here our network address is :/0. Our next hop is going to be our connection to the internet, which was, I looked that up on the paper here, 2001 470 C3271 :2. All right, so that now is our connection to the internet. Let's make sure now that we can ping IPv6, make sure we can ping our gateway to the internet. So I'm just going to copy and paste that, make sure, and sure enough, we get 5 bangs there, means we have success. All right, let's make sure we can ping out to the internet. All right, there is an IPv6 name server that we use. I'm using the one directly from Hurricane Electric. So ping IPv6 2001 470 20 :2. All right, so this is the name server for IPv6 at Hurricane Electric, and I can ping that address as well, which means I'm connected to the public internet now. Perfect. I set up my router by putting IPv6 addresses on both of my interfaces, okay, and then I turned on IPv6 unicast routing and set up my default route. I think we're pretty much done on the router now, so I'm going to minimize this window. And now what I want to do is I want to take a look at my client configuration, because IPv6 does something pretty nifty and kind of crappy. All right, it's nifty and crappy at the same time. If we do ipconfig here, I know none of you type as badly as I do here. If we look at our IPv6 address, all right, we're actually using this temporary IPv6 address. That's what Windows uses. And look at that, 2001 470 C327A, and then I have this weird host portion. Well, what's happening here is that in IPv6, we do not need a DHCP server. All right, we do not need a DHCP server, because what's going to happen is the router is going to send out these periodic router advertisements. The router advertisement is going to say, hey, I know how to reach network 2001 470 C327A. Now go configure yourself, client. And what Windows does is it randomly chooses a host portion for the address, right, this last 64 bits. It randomly chooses a number, and then it uses that to communicate out to the public internet. So right now, I should be able to ping 2001 470 20 :2, because that is my DNS server out on the public internet, right? And I get a reply from that. So really, this is all automatically configured. And this is the dangerous part about that and the cool part about it. Let me go into my ipconfig and add in that DNS server into my IPv6 configuration. C32, 20 :2. All right, and what this is going to let us do now is it's going to let me open up the internet, and I can open a new session. I can go to google.com. All right, brings me right to google.com. To make sure you understand this, I am running only IPv6, okay? If I look here, I do not have IPv4 address. I have the auto configuration IPv4 address, and I have no default gateway. I have no default gateway for IPv4. So I have no way of getting IPv4 traffic off of this network, okay? So I'm only using IPv6 right now. If I go to news.google.com, all right, we get to see all the awful stuff happening in the world right now. And the sad part about this is that most of these news sites are, even though we can see them on the Google website, Google is translating it and putting it into an IPv6 website for us. If I were to click on one of these links, let's say Google Glass gets a makeover here, right? I go to this other page and it says, page isn't available. And that's because this other entrepreneur website that I clicked on is using IP version 4 only. All right, and if we click around a lot on these websites, almost all of them that we link to from Google News do not give us an IPv6 load. All right, we cannot load these sites in IPv6. Here we go. Information Week looks like it has a partial IPv6 capabilities. All right, we start to get these weird situations happening here. So the one last thing, I want to show you here. People get creative, like Facebook did. If I ping facebook.com, we are always going to use IP version 6 addresses first. All right? So when we're pinging facebook.com, we can look at the address, and Facebook did something kind of nifty here. What they did was they changed their host portion to have Facebook in it. So you can actually put words in there because we're working with text. As long as your letters in the alphabet are A through F and 0 and 1, you can write quite a few words there. Let me wrap up the summary here. I don't see any questions that have popped up, which is great or not. If you have some questions, let me know what those are. I can always get to them in a Twitter feed later, or I can do a blog post to reply to any questions that you have. All right, so let me wrap this up with our summary. So my first recommendation here is set up a test lab. Go to hurricaneelectric.net, get your IPv6 address space, set up your test lab, build an IPv6 only network. See how that works, all right? Build an IPv6 only network. This is going to take a lot of the fears you have out of how IPv6 is working and what's available on the internet and what isn't available, all right? If we send traffic out with an IPv6 packet, we're only going to be able to talk to other devices that support IPv6, okay? We cannot talk from an IPv6 device to an IPv4 device without a lot of messy translation. So set it up, observe it. Use Wireshark. If you haven't used Wireshark yet, get in and do a deep dive with Wireshark. I'll have a course coming out very shortly here about an introduction to Wireshark on the Pluralsight site. Keep your eyes out for that. And you can learn some Wireshark stuff too. All right. After you get your IPv6 network set up, add your IPv4 back to it and dual stack it. All right. And I see Eric here has a question. It says, do you have a blog post detailing the Cisco setup of creating an IPv6 and IPv4 network? No, I do not. If you do go through my, spit it out here, Ross. If you do go through my video series, I do have like a lot of test labs that you can set up there. But that's a great thing. I can set up some kind of blog post about how we can configure our Cisco router for IPv6 connectivity. I might even be able to do a little demo of IPv6 hooking up to Hurricane Electric. Chris, I'll come back to your question in just a second here. All right? So the second thing is you're going to have to be extremely cautious on your production networks. All right? I didn't tell you a lot about what to be cautious about here, but IPv6 is natively turned on most devices. Okay? IPv6 network connections are attempted before IP version 4 connections. All right? So if you have a network set up, and let me jump to this next slide here quick. Right? If we have this IPv4 network set up, and maybe we're connected to the IPv6 internet over here, and we don't set up any IPv6 in any of our devices here, and then we turn on a global unicast IPv6 address here that has the potential to talk to the public internet, what could end up happening is we can end up black holing all these devices, and these devices may actually get very, very, very slow because it's going to try to use IPv4 first before it's going to use IPv6 first, which it has no route to get to the internet for in this case, right? It's going to try that first, time out, and then use IPv4. So we can actually end up causing some damage if we're not cautious in our production networks. That's why I say set up a test lab. Set up a test lab and play with this first, okay? The last part here is keep it simple, all right? Keep it simple, stupid. Use /64 for all your network segments. Don't worry about wasting addresses, all right? And aim for a good route summarization and organization of your network, right? Don't try to build this upon IPv4 design criteria. What you want to do is design it good for IPv6. And in my experience, the best way to do this is to literally just play with it. All right? I'm a little tiny bit over time here, but I want to answer Chris's question because it's easy enough. It says, what would happen if we went to a site that tells us our IP address? Let's see if What's My IP works. And it looks like What's My IP is not for IPv6. So let's try What's My IP, IPv6. And let's see what we get here. Look at that, 2001, 470, C, 327A. All right, and let me pull up my command prompt so we can see if that's the host portion of the address that I said. We'll do ipconfig / just ipconfig is all we need. And I said it should be this temporary IPv6 address, and that is what it is, it looks like. 9C56D0811D2F117. So it looks like it's when we do a What's My IP, it's showing you your public IPv6 address. Okay, hopefully that answered your question, Chris. Tom says, is it possible to get independent addresses, provider independent addresses? The answer is I do believe it is. In the U.S., under ARIN, you have to go to ARIN's website, ARIN.org, or ARIN.net. And on ARIN.net, we should see there's a way to apply on there to get your own autonomous system number. And once you have your own autonomous system number, then you can get your own provider independent addresses. Be cautious with getting your provider independent addresses because you're going to have to talk to some ISP at some point to make sure that they will peer with you and transfer your provider independent addresses within their network. All right. Hopefully that answered your question, Tom. Last question here, and then I need to wrap it up. Why are there percentage signs here in our addresses? These, as I understand it, these percent signs are a priority. All right. This is a priority value on IPv6, especially in Windows. I do believe this shows up in Linux and Mac and whatnot as well. What we're going to find out with IPv6 is that we can have multiple IPv6 addresses on our interface that are on different networks. As a matter of fact, we can have up to 5 IPv6 addresses on any network interface card. Well, if we can have 5 IP addresses there, how do I know which IP address to use, and how do I know where to go? And it's my understanding that we can set those priorities up, and those priorities will show up with this percent value. So I thank you guys very, very much for participating today. Hopefully you got a lot out of this. And hopefully you got enough out so that you want to go back and watch my networking videos now and learn more about the really cool world of data networking.